Hi everybody. This will be a quick little video tutorial on BondEnergies. Now, I'm going to get right into it. The purpose of BondEnergies is to help us predict whether a reaction is going to be exo or endothermic. So we would use this type of method to do a theoretical calculation when performing a reaction in a calorimeter is not feasible. So if we know what the reaction is, but it's unlikely that we can actually conduct it safely or conduct the reaction in water without a competing reaction happening, we would do this technique here. Okay, so with this, you can predict the amount of energy any reaction is going to produce, and here's the thought process behind it. So to start off, bond dissociation energy, which is a term with the variable d, is the energy required to break a chemical bond. Now, remember what a chemical bond is. It's an overlap of orbitals. All right, so you're not breaking it like a glow stick. You're physically just pulling two atoms apart away from each other, right? And the amount of energy it takes to do that is what the bond dissociation energy is. You have to overcome the attractive forces, right? It's also equal to the amount of energy released from the bonds when they form. So when bonds form, they become more stable and they release energy. We talked about the idea of molecules calming down, right? So you need to put that energy back in to separate the bond, right? So if two bonds come together and release 10 kilojoules of energy, to separate them, you have to put that 10 kilojoules back in to put them on their own. All right, so next point there says the bond energy is an average of the bond within a molecule. So there's many different types of bonds. It's affected by what's bonded around it. So we just use an average value that's given to us. All right, multiple bonds have more energy than single bonds, so multiple bonds are stronger and shorter than single bonds. So we'll use carbon for an example. You can have a single, a double, or a triple carbon bond. We don't do quadruple bonds. They don't exist within these types of bonds, right? So the strongest one will be the triple bond because they're so short, the nuclei are so strongly overlapping with each other, not the nuclei, sorry, the orbitals, that it takes more energy to separate them. Right? Imagine more links holding things together. You need more energy to break those. So because it's an energy value, it can be used to determine the change in enthalpy of a reaction, since bonds are broken and products are formed. So energy is added in order to break a bond, and energy is released when bonds are formed. So we have the idea of endo and exothermic within one reaction. So the energy change, the total energy change, is the sum of the energy required to break the bonds minus the sum of the energy required when the bonds are formed, right? That's released. So here's our equation, right? And now as long as we know what the substances are, we can predict if it will be endo or exothermic. So let's try an example of this. And keep in mind, when bonds are broken, those are the reactants, and the products are the new substances formed, so their bonds form. All right. So we'll calculate delta H when H2 reacts with F2 to form hydrofluoric acid in the following equation, and it's balanced for us. Now the bond energies, I'll scroll down here, are given to us in a chart. Okay, so we have access to all of these. All we need to know is the structure of each substance because it's a bond energy. So we draw a Lewis diagram for each. We have H, and then we have two of these molecules here that we need to keep in mind. So those are all of the bonds. We have one hydrogen-hydrogen bond, we have one fluorine-fluorine bond, and we have two hydrogen-fluorine bonds. Okay, now these are different than intermolecular forces. So as a calculation, we can say this: delta H is equal to the sum of the bond energies that are being broken minus the sum of the bond energies released from the formed products. Okay, so that's going to be equal to, we'll put big brackets here, 1 times a hydrogen bond, and okay, so we'll put square brackets around that, that's one reactant, plus, we'll use square brackets again, 1 fluorine-fluorine bond, okay, and that's all of our reactants, so we'll close our brackets here. So that's the sum of the reactants, minus, because the energy is released, and we only have one product here, so we'll say 2 times the hydrogen fluoride bond. Okay, and if there was more than one product, we would add them all together, right, and make sure that those are our products. So we'll substitute our numbers in here. We've got 1 times, and then going back down to the chart, If we look at HH, it's right at the top here, 432. So we say 432, and if you look at the units here, it's in kilojoules per mole. Right? That's why we use the number of bonds. Okay, and we assume that that's there. Say 1 times the fluorine-fluorine bond. I'll go back to the chart. Right, and we scan through it, and you can find it in the second column at 154 kilojoules. Right. So we'll sum those together, then we'll subtract 2 times the HF, which if I go to the chart here, it's right near the top, 565, and that's kilojoules. Okay, so when we add that up, what we find out is that we get a value of negative 544 kilojoules, which is delta H. So we can say when this reaction occurs, it will be exothermic. Right, and that's the idea behind it there. So we've got example 2 here, right? And what's important is the structure of each before the actual reaction. So we look at the coefficients. Fluorine is simply a single fluorine bond, and we've got 2 of those. We've got 2 chlorine single bonds. We've got methane, right? And if I draw methane off to the side, okay, so we'll need to use our Lewis structures. There are 4 carbon-hydrogen bonds. So you're not going to find a methane bond. It's just what it's made up of. Now for difluoro-dichlorocarbon, if we look at that here, that's essentially methane substituted with halogens. Right? So what we have is 2 carbon-fluorine bonds and 2 carbon-chlorine bonds. So you really need to know the structure. Then we've got 2 hydrogen-fluorine bonds, and lastly 2 hydrogen and chloride bonds there. So that's the important part, because now when we go to here, we take all of our reactant bond energies, add those, add all of our reactants or product energies, and then find the difference between them. So we'll start off with this, the sum of the broken bonds minus the sum of the formed bonds. Okay, and all the values are in the chart below. Just going to kind of simplify this here. So we've got 2 times the fluorine bond, which is 154 kilojoules, plus 2 times the chlorine-chlorine bond, which is 239 kilojoules. Okay, and just for simplification in this, I'm leaving out the equation. Then we've got 4 times the carbon-hydrogen bond, which is 413 kilojoules. Now that's all of our reactants. Okay, so that's all the energy that they release. And we'll subtract from this the product energy. So we have 2 times the chlorine-fluorine bond, which is 485 kilojoules. We'll go on to the second line here. Plus 2 times the carbon-chlorine bond, which is 339 kilojoules. And I'm getting these numbers from the chart. I've just got them written out in front of me here. Plus 2 times the hydrogen and fluorine bond, which we used up here. So you can see that that's 565 kilojoules. And then finally, we've got 2 times the hydrogen and chlorine, which is 427 kilojoules. So it's a slow process, and we don't use this because there are quicker ways that we're going to learn. Okay, but in the end, what we're going to get for the reactants, right, they release 2,438 kilojoules. The products require 3,632. So when we subtract those numbers, we get a net value of 1,194 kilojoules. So this reaction is also exothermic, releasing quite a bit of energy. All right, and keep in mind, this is not molar enthalpy. This is enthalpy change, so we would be able to specify that per substance reacted. So I'll leave that there. If you need to pause and go back, go ahead. All right, the last example to kind of go through is determining the enthalpy of 1 mole of ethine. Okay, so we would do the exact same thing here because we have no information. All we have is a balanced chemical equation. The broken bonds minus the energies of the formed bonds. Right, and if we look here, we would need to draw the structures. I'll leave these off to the side and allow you to try them. Okay, so the structure for ethyne is given there. Oxygen, you can draw that yourself, but there's its bonding pattern. CO2 and H2O. So once you know the structures, right, you can find the number of bonds. So we have carbon triple bonds here and carbon hydrogen bonds separately. Then we have carbon oxygen bonds, carbon oxygen bonds. So if I list them for all of the reactants, it'll be 1 times the carbon-carbon triple bond plus 2 of the carbon-hydrogen single bond. And then there are 5/2, so we can just put the coefficient there, which is like 2.5, of the oxygen double bonds. So that's that. That's reactants. Plus our products, which were, we had 2 of the carbon-oxygen double bond, right? 2 of those per molecule, and there were 2 molecules, so we need to factor that in as 4. And then there's 1 water molecule, which has 2, we just kind of write this out, of the oxygen-hydrogen single bonds. So using the values that you get there, I'm just going to simplify this. I'll allow you to try that. Negative 1,227.5 kilojoules for the entire reaction. Okay, so that's the enthalpy change. And then for molar enthalpy of combustion, it's delta H divided by the number of moles. In this case, we're using ethyne, which is C2H2. So we just say negative 12.7.5 kilojoules divided by 1 mole of ethyne from our balanced chemical reaction, and we get our molar enthalpy here. So we get per mole of ethyne, not per mole of anything, just per mole of ethyne. So when we combust ethyne, that's the amount of energy released from that reaction there. Okay, so there's the energy in the bond table. You can kind of print those and have them for yourself. There's some practice questions below here, and then a little note on ranking the energy changes associated with different chemical processes. So hopefully that was helpful, and good luck with those.